So the screen is visible to you, I hope. Can you see?
Yes, sir.
Okay, so we have uh, done this much, and then this was the complete block diagram of the frequency control system. Then we have performed the analysis and found the steady state frequency uh, error, steady state frequency drop. Following a low change in demand, how much will be the deviation in frequency from the rated value, from the set value? And that is given by this expression. And also implication of this expression we have described, we have discussed how much the active power will change, active power generation will change because of this change in frequency, how much will be the change in the consumption in the load, and what is the load frequency characteristics of the total system. That also was discussed. And also we have discussed how the system is supplying power to a newly connected load just at the instant of connection, at the new steady state, and also in between the instant of connection and the arrival of the new steady state. So how the new load is getting power. Okay, that those things were discussed. Okay, now what you have seen, you see that say initially the system was delivering a certain amount of power, say this much. Okay, this is delta PD showing. So here the load is 0, here the load is 100%, and variation in demand we are expressing as delta PD. Say this much was the value of demand. Okay, and obviously according to these characteristics, this will be the operating frequency then. Okay, and frequency will vary from here at no load to here at the full load condition. In between somewhere, this was the operating point at a certain instant of time. So this was the frequency and this was the power delivered to the load. Okay, now if the load is increased, load increases, somewhere it is here. So you see that according to these characteristics, this power will be delivered by the generator, but frequency will be somewhat less than the frequency that was there before the inclusion, before the switch on of this load. That means as the new load is switched on, frequency will actually decrease. Okay, as the load increases, frequency will decrease. As the load decreases, frequency will increase. So this indicates that frequency cannot be kept constant by the system if this particular operation is maintained. What is this particular operation? You see here, we have assumed that del PCS is 0. That means there is no change in the position of the speed changer. That means no external effort is given to maintain the frequency. Then how the frequency is controlled, how the frequency is regulated? This is done by the governor alone. Governor on its own is sensing the change in frequency. As a result, it is changing the output of the opening of the steam valve, and so the generation is changing, and this is how the frequency is being maintained. And with this, what will be the range of frequency variation? You see that this gives you the range of frequency variation. How much? That is given by that is basically given by the governor regulation. And here, if you include everything, that is given by this character b plus 1 upon r. That means 1 upon b plus 1 upon r. This will give you the range of frequency variation, considering that governor alone is operating. Governor is controlling the supply, controlling the power output of the system. Okay, so and then frequency is bound to vary, assuming that 4% is the governor regulation and 50 hertz is the upper nominal frequency. Then frequency variation will be around 2 hertz because 4% of 50 hertz means 2 hertz. So from the no load to full load, variation of frequency will be 2 hertz. So obviously, this much of frequency change will not be permitted in any practical system. So it has to be improved. Frequency has to be regulated within a narrower zone. Okay, frequency will be changing, but it should change within a very, very small zone. Okay, so this will not be an acceptable situation. So how this can be improved? This situation may be improved. We want that, you know, that in a power system, load is always varying. You know the load curve. Throughout the day, sometimes load will increase, load will decrease, but with the change in demand, if the frequency varies, so obviously you cannot have a control over the operating frequency of the system. So a better situation is needed, and how this better situation may be obtained, that may be obtained by the application of this supplementary control, or the so-called secondary control. Sometimes it is said. What is the secondary control? Here you see that this much was as before. Okay, this was the governor and turbine transfer function. This is the power output of the turbine. Then this is the change in demand. This is the power system including the generator and load. This is the governor regulation, and this much was there. Del PCS was there, but we have not given any input to del PCS. Now an input is given here to the del PCS. That means somehow we are changing the position of the speed changer. Means actually a command is given either to increase the power output of the generator or to decrease the power output of the generator depending upon the situation. And what type of input is given here, whatever control is being implemented here, it's shown here. You see that it is Ki by S. Ki obviously will be the gain. Okay, gain of the controller. This, it is representing a controller. Gain of the controller is Ki, and 1 upon S means obviously the frequency error is integrated. It is delephased by S. Frequency error is integrated or it is accumulated and given as input to the speed changer. So what you can see, this is the representation of this supplementary control where frequency error will be integrated. That means integral control will be applied to change the position of the speed changer. And if this integral control is applied, you know that when the integral control is applied, then obviously the steady state error becomes zero. From control system theory, you know this. So now, if you find out the expression for del Fs, obviously you can find it out from this block diagram very easily. You can find it out. You can assume a change in demand, okay, and change in del Fs, change in the frequency. You can calculate and you can find out the steady state value of this change in frequency using the that final value theorem. You will see that that steady state error is zero actually. Okay, that steady state error is zero. So what does it mean? We shall explain how this steady state error, that this error is becoming zero. What does it imply? How we can explain this? But before that, let us see. Let us come back to this. Actually, the group characteristics of the system. So if the supplementary control is applied, or that means the integral control is applied, then from control system theory, you know that, and also if you find out del Fs and you find out the steady state error here after implementation of this integral control, you will see that at steady state delta F is equal to zero. That means it indicates that after the variation in demand, frequency will be back to its nominal value. Frequency will come back to its normal value. That means it is possible. When it is possible, if you give an input to the speed changer, and that input has to be following the integral control. Okay, so what does it mean? If the integral control is employed, say if this was the operating point and this was the load. Now it means that after you have increased the demand, say here, load has been increased up to this point, then this should have been the operating frequency had there been no change in the speed changer position. Now, with the change in the speed changer position, what you can see, delta f becomes 0. That means frequency is coming back to this position, normal steady state. This frequency is being restored, and this frequency is restored at this load. Means what is actually happening, if we draw a perpendicular line from here, then you see that, and also a line for frequency error, and that means somewhere here is the operating point. An operating point obviously should lie on the characteristic system load frequency characteristics. It cannot be outside that. That means that these operating characteristics, as if it had been shifted from here to here, so then it has been shifted parallelly, because slope cannot change. If the value of B is not changed, if the value of R is not changed, R you cannot change because it is the governor group. Governor regulation. It is the design parameter, you cannot change. B obviously will depend upon the composition of the load. If we assume that composition of the system load remains same, then obviously B also will remain same. Then it means that in order to maintain the same frequency at an increased demand, say here, if this has to be the operating point, then this operating point must lie on this characteristics. Means this inclusion of this speed changer input, okay, has actually shifted this characteristics from here to here in this way. It has been shifted parallelly from its initial position. Means integral control is basically shifting the group characteristics, system load frequency characteristics from its initial position in the parallel direction. Okay, it is parallelly moved. This is the impact of the speed changer input. Am I clear? Could you understand this? Basically, frequency is kept constant. After the change in demand, frequency is coming back to normal position, normal value. Because delta f from integral control, due to integral control, delta f at steady state becomes 0, means original frequency is restored at the new load. So when the new load with the increased demand, if the original frequency is maintained, that operating point must lie on the load frequency characteristics of the system. And this is representing the load frequency characteristics, basically this slope. It has to be kept constant. That means what is happening? Actually, the integral control or the change in the speed changer position basically is shifting these characteristics from here to the new position. And it has to be moved parallelly because slope cannot be changed. Means the impact of the speed changer input or impact of the integral control is to move the load frequency characteristics in parallel direction with respect to its initial position. Okay, this is the impact. So could you understand what does it mean? What it implies? How frequency actually the integral control is changing the you can say the position of the load frequency characteristics, maintaining its slope. Is it clear?
Yes, sir.
Okay. Now let us see how this is actually implemented. So here basically integral of frequency control means frequency error means accumulated frequency error. That means collected or accumulated frequency error, integral of frequency control. So what is actually done basically that is system time compared with standard time. Basically what is done, actually this supplementary control, this is an additional control, that means how to change the position of the speed changer. This control actually will not be implemented in each and every power station. Each and every power station is having this inner control through governor, because governor is installed with each and every generator. Okay, that is the primary control, so-called primary control. But this additional control, supplementary control, this is actually implemented in a single power station, say in large power station in case of a large power system, or maybe with a single generator in case of a small power system. And that particular generator or that particular power system is having the responsibility of changing the position of the speed changer and accordingly maintaining the frequency of the power system. That means to bring the frequency back to original position. It is the responsibility, or this responsibility is imposed to a single power station in case of large power system, or to a single generator in case of a moderate size power system. Okay, and how this is implemented? So in that power station where this supplementary control will be implemented, there they run a clock. Okay, and that clock is run by the power system supply, the power supply. So obviously that means the system frequency will be responsible to show the time in that clock, which is called the synchronous clock, because the power system, that means the synchronous generators are there. The generator is running at synchronous frequency. So that clock is known as the synchronous clock. The synchronous clock will be showing time in the substation on the power station where the frequency clock will be implemented. And that time will be compared with the ordinary clock. Or that time we can say that is the system time. That means the synchronous clock is showing time. Obviously that time is generated rather by the, or that time is being shown by the uh, system frequency. That's why it is called the system time. That system time is compared with the time shown by the ordinary clock. Ordinary clock will show standard time. So if the system clock is showing positive error, that means the time shown by the system clock is in advance of the actual time shown by the ordinary clock, then it means the frequency is actually above normal. Okay, that means the collected integral of time frequency, that is nothing but the time. That means the frequency is, or frequency error is positive, frequency is above normal. If the system time is behind the actual time, ordinary time, that means the time given by the ordinary clock, then it indicates that the power system frequency is less than the normal frequency. And this arrangement, this control will actually change the position of the speed changer, and that will be changed automatically. Automatic arrangement will be made, is made there. So if a predetermined time error is actually exceeded, the pre-accumulated time error, when it exceeds 3 seconds, then speed changer position will be changed by 1 step. Okay, so accumulated frequency error, and how this frequency error is accumulated frequency error by measuring the time, system time, and comparing it with the time given by the ordinary clock. What is the system time? System time means the time shown by the frequency clock. Okay, what is the frequency clock? Frequency clock means a clock that is run by the power system supply. So this clock will give a time depending upon the frequency of the supply. Okay, frequency of supply will generate the time here. So this is how the time frequency error will be integrated and given as input to the speed change. So you see that if this is implemented, then what will happen? The steady state frequency error will be 0. That means frequency will be coming back to its initial value, to the original position after the variation in demand. Maybe it is the increase in demand, or maybe it is the reduction in demand. This is how the frequency control will be done. So how the system is controlling the frequency? Initially, after the change in demand, all the generator in the power system, depending upon their governor action, will actually take part in the increase or decrease of generation, because this is first. The primary control, this inner control, inner loop control, this is first. This depends upon the operation of the governor, time constant of the governor. Time constant of the governor is much less than the time constant of this secondary control. So the governor associated with each and every generator will take part in control of frequency, okay, depending upon their regulation after a change in the power demand. Okay, so obviously frequency will deviate from its normal value, and frequency will be actually uh, away from its nominal value as well. But when the integral of frequency error measured by this system time, it exceeds a certain predetermined value, that means let's say around say 3 seconds or so, then the speed changer position will be changed by this secondary control or supplementary control by one position. As a result, what will happen? This particular generator or this particular power station where the speed changer position has been changed, it will actually generate increased amount of power or decreased amount of power depending upon the increase or decrease in demand. So if there had been some increase in demand, then speed changer position has been changed from this power station that is responsible for the control of frequency. So it will increase its power output. So as it increases power output, what will happen? All the other generators will then be correcting their generation. Okay, since this generator has increased its power output, so all other generators will now be okay restoring their initial setting value, generation in their initial setting value. Actually, this total function of maintaining the frequency is an integral part of frequency control as well as so-called economic dispatch. This economic dispatch, or that is called the uh, generation scheduling problem. This is actually this perhaps will be taught by the other teacher in the other section. Perhaps this has not been done yet, but it will be done. You'll see there that generators in power system are to be operated in a controlled manner such that total cost of power generation may be kept at a minimum value. Okay, so the total cost of generation is minimum. Obviously, a given power output may be obtained from a number of generators in many different ways. Many different combination of power output may be obtained or may be achieved for a number of generators working in a power system. So we shall be operating the generators in such a way that the total cost of operation becomes minimum. And this way, and generating the operating the generator in this way is called the problem of solving the problem of economic dispatch, generating or dispatching power in the most economical way. In this case, that means in the economic dispatch, what you do, you are changing the power output of the generator. In the frequency control problem also, you see that you are actually changing the power output of the generator. Here the intention is to control the frequency. There the intention is to minimize the cost of generation. And these two problems together is called the automatic generation control. The problem of automatic generation control, or simply somehow sometimes it is referred to as AGC, automatic generation control, AGC. Okay. So what is happening here? Initially, all the generators are operating at their predetermined power output value, and that predetermined power output value is also changed from time to time. This is the part of the total system control that we cannot discuss here because it will be a larger problem and will be discussed in the obviously it will be discussed to those students who will be actually taking power system as elective paper. Okay, to them this will be discussed. So basically, as the system load changes, the overall system control system, the control system to control the overall power generation, they actually calculated a power output value for each and every generator. And each and every generator then operate their power output, deliver their power output at that calculated value of power. Okay, and maintain the system frequency. Now, say system is operating at that calculated value of or the set power output value. Now the load changes. So if the load changes, obviously then immediately the governor system frequency will be deviating from the normal value. Governor associated with the generator will actually operate on their own. So as a result, generators also will deviate from their set power output. Okay, with the increased power demand, all of them will generate somewhat increased power output. So as a result, frequency will decrease. Okay, because we have seen that switch governor action, that increase in power output of the generator is possible at the cost of reduction in frequency. So frequency will decrease, power output will increase. Now, after some time, that supplementary control, okay, or secondary control through the speed changer, which is assigned to a single power station, say, okay, that will be in operation, and it will restore the frequency back to initial value, and for this it will be generating somewhat more power. It will be delivering more power to the system. As more power is being delivered by the generator, other generators will now be restoring their initial power setting value. So in this way, generators will be able to operate in the most economic value, most economic operating condition, and the system frequency also may be actually controlled. Okay, system frequency also may be controlled. So finally, you can see that frequency control is the responsibility of this generator or of this power station, where the supplementary control will be implemented. But initially, as the system load is being changed, all the generators are deviating from their initial setting value. That means they are following the load. So they are taking the function of load following. It is called the load following. That means they are following the load. Following the load, they are changing their power output. When there is more demand, they are increasing their power output and at the cost of system frequency. But that is for a small time only, for a very short period only, because after some time, when the supplementary control will be activated, okay, then the frequency will be brought back to its initial value, and then all these generators who had initially changed their power output setting or change their power output will now be uh, restoring their initial operating condition. So this is how the frequency of the system is being controlled through supplementary control action. Okay, this supplementary control sometimes is called the secondary control, because this control is called the primary control. Initial and primary control is obviously faster. It is faster because its time constant depends upon the uh, time constant of the governor only. It is slower because the secondary control or supplementary control is slower. Why it is slower? Because you have to integrate the frequency error. You have to accumulate the frequency error. Since accumulation is there, obviously it will take time. So supplementary control or secondary control is slower compared to primary control. Okay. So, and this analysis is there here. Del FS is being concluded. It's going to very easily do this. Okay, and that whatever I actually told you, that let us see or follow this one also in support of my discussion. Supplementary control shifts the characteristics parallelly. Already I have mentioned, because what is the action? Supplementary control is restoring the frequency back, and the operating point must always lie on the system frequency characteristic. That's why you can see that the role of the supplementary control is to shift the load frequency control characteristics in parallel to its initial value and maintains system frequency irrespective of demand. So therefore, it is the function of the supplementary control to maintain the constant frequency. Okay. And generally, it is applied to one generating unit for a small or medium-sized power system, and applied to a power station or large system. For a large system, it is applied to a single power station. For a small system or medium moderate size system, it is applied to a single generator. So this is how the frequency control is being done. Load following by older machines. Load following, basically following the load. So what is the in this process of frequency control, what is the role of the individual generators who are operating on the action of their governors. They are basically following the demand. That's why, as if they are performing the function of load following. As the demand is increased, they are increasing their output. As the demand is decreased, they are decreasing their output immediately. So they are performing the load following actions. So particularly, these can be done by the older machines. This function of load following may be done by the older machines. New and efficient ones can run economically. Since already I mentioned that the changing the power output and controlling the frequency, this total function is called the automatic generation control. So in this way, what we can do, we can actually allow the newer machines, which are more efficient machines, to operate at their uh, set power output. In this way, they will be actually performing the frequency, they're performing the uh, maintaining the system economy. Okay, so older machines may be following the load following, may be performing the load following actions, and newer machines can be used to run economically. So this is how the speed control is being, or frequency control is being implemented. Okay, so basically this much was to discuss regarding the frequency control, and then what is left, this will not be included in the, though it is there, but this will not be not a part of your it was you can say that load frequency control discussion for your purpose. Okay, this will be for some other purpose. So this is regarding the supplementary control. And now let us you see whether you can understand this one or not. Okay, and if this is understood, then I shall actually discuss some other thing related to frequency control, and the frequency control basically implemented in our power system. Okay, that part I shall discuss, which is not a part of our curriculum, obviously, but that is interesting. We are discussing the frequency control. We must that discuss that thing as well. Okay, for completeness, that thing also should be discussed. That's why I shall discuss this. So, could you understand it? How speed changer position will be changed using the supplementary control? Is it clear?
Yes, sir.
Okay, now let us now discuss. So this completes the discussion on frequency control. What we had to discuss in respect of frequency control, that is this much only. Okay, I shall be actually discussing some numerical examples. So I shall have to take a PDF of those examples. Then only I can discuss. Currently, this is not PDF has not been prepared, so I cannot discuss this today. Okay, so on some other day I shall discuss those problems as well, along with some other problems, related problems. Okay, now let us discuss regarding the frequency control, how it is implemented, how it is actually done in our system. This control is there, obviously, but additionally there is some other control, because unless this control is implemented, supplementary control is implemented, you cannot bring the frequency band to normal value. But in our system, frequency control includes some more thing. What is that more thing? That is the a tariff system. Tariff means how we will be pricing your power. Okay, how the electricity price will be decided. That is the tariff system. That tariff system is called the ABT, availability based tariff, and that tariff system is implemented for bulk power consumers. Okay, well, who are these bulk power consumers? Actually, what happens, we are all small power consumers connected at the distribution system. Okay, but there are, you can say that if you think of that, there are different power supply companies or supply system power supply companies. Previously those companies were known as the basically state electricity boards were there previously, but nowadays there are no such state electricity boards. All those boards were dissolved, and now a separate generation company, transmission company, and distribution companies have been actually created by breaking up the electricity state electricity boards which were there before say 2002. there were electricity board in our country, and this was the system, you can say, almost everywhere in the world also. Okay, but there had been some change in the operation of electrical system throughout the world, and that change has started in 1988, you can say, and that change is popularly referred to as the deregulation or restructuring of power system. Okay, after that deregulation and restructuring of power system in our country, that has been started actually around 2002. Okay, that has been started in our system, and there was electricity bill 2003 was passed in our system, and according to that bill, all the electricity boards were dissolved, and separate distribution company and power sub-generation company were created, and transmission companies were also created. Okay, the basic purpose was to introduce competition into the system, because competition makes system more efficient. Whenever there is monopolistic system, there is inefficiency, and that's why people thought that everywhere the people thought that electrical systems were somewhat inefficient. Okay, was due to the lack of competition, because in the older day power system there was electricity board, and the role of that electricity board was to generate power, transmit power, and then to distribute power, and everything under one single company. They were supplying power to that total geographic area of their actually network. Okay, this was the system. So, but the system has been dissolved, and therefore electricity company were developed, and this electricity company now they can actually sell and purchase power. Like previously also electricity board could sell and purchase power, say this electricity board, that electricity board, along with some other electricity companies, says like CESC, say like DBC, those were separate entities, separate companies, those were also there. They had their own generation, though some of them had transmission, some did not have. Some of had a generation as well as distribution. CSC particularly say mostly distribution and on very small part of small generation. But similarly, DVC, they had their generation, they had their some transmission as well, and okay, so these systems were there. So these generate power utilities previously, and then power companies nowadays, they can sell and purchase power. If a generation company is there, it can generate power and sell this power to some other company who will be purchasing that power. Okay, and who will be controlling the total system, and there is the total system will be controlled by some other body, some other organization, say. So, in earlier days in our system, it was obviously the government was the owner of this all these things. So, and there, the system when these companies were selling power and purchasing power, there was a different tariff. Then that tariff was implemented for them only, for some generation company, for some power utility. They generated power, they purchase power, at what rate they will purchase power, at what rate they will be generating power. There was some rule were there, and those rules, basically those tariffs were there. A part of those tariffs were that basically if you have a say certain amount of power generation, installed power generation capacity, you must maintain a certain amount of plant load factor. Hmm. Around say 62.5% plant load factor you must maintain. This was the regulation previously then. Before this new tariff was implemented, that is related to frequency now. This tariff is implemented since 2003. Before that, the tariff was such that for getting your full revenue by selling power, okay, you have to maintain a certain amount of plant load factor. Means what is that certain amount of plant load factor? That was around 62.5% plant load factor. What does it mean? Means what is a plant load factor? Obviously, you have studied regarding the plant load factor. That means if you have a capacity of say 100 megawatt, that means you must generate power, and actually your plan should be operating in such a way that you are utilizing at least 62.5% of your capacity. This, in simple sense, or in simple way, if I say, this is the meaning of plant load factor. Okay, somehow, if you have 100 megawatt capacity, declared capacity, say, you should maintain, say, 62.5 megawatt at least. This much of capacity must be utilized to supply power. Unless you supply this, you give this, you will not be getting your full revenue that you should earn by selling power to the power system. Okay, and you will be penalized while you will be selling power, or you will be penalized while you will be purchasing power as well. Okay, so previously this was the rule, and problem of the electricity system in our system in those days. If you see the frequency of our system before 2002 2003, okay, if you see the network, if you see the, oh, sorry, net, you will see that you will be getting the picture of those days frequency, which was actually varying from to a wide range, say 47 hours sometimes when the load is low, and when the say frequency is, sorry, when the load is high, it is say for 47 hours. When the load is very low, say it is 52 hours. This much of frequency variation, wide range of frequency variation was there. So that was a problem, maintaining the frequency. Because from the discussion in frequency control, perhaps now it is evident, now it is clear to you that what is the sole reason for frequency variation? It is the unbalance between the power supply, that means unbalance between the power generation and the power demand. This is the sole reason for frequency variation. So, and why this was there? Because the tariff system previously was such that those who were purchasing power, they were actually extracting power from the system without any notice. Okay, say you have a transmission line, so you have some load, you can draw power from the network. You have connected to high voltage network. So say at your home also. Okay, say you are supposed to draw, say, at most 5 kilowatt power from the system. For example, say. Now, if you draw more power, who will be restricting you? Unless your fuse is burned, obviously nobody is there to restrict you. You can easily, if you go on connecting more and more devices, those devices will get power from the system. Is not it? Would you understand my point? That means if you connect more and more devices at your home, say you have a 5 kilowatt is a capacity, you should the license is such that, or you are permitted to draw 5 kilowatt at most. But you have connected so many extra power, so many refrigerators, okay, so many ACs are connected such that, and obviously the total power will be consumed from the system. Nobody will be there to restrict you unless the fuse connected to your power supply is actually is it is made, you will be getting power. That means unless the now the MCs, okay, that is tripping, you will be getting power. Okay, and that happened with the bulk power company also. They were say they were supposed to draw some power, and that power generally is the negotiator. Previously they had to declare that I shall be drawing this much of power from the system and I shall pay for that. But say there was a agreement that this particular company will be drawing some 100 megawatt from the system. But now, since its load has now increased, it is say drawing some 120 megawatt. Then who will be restricting it from drawing this power? Nobody can, because there was no such regulation to maintain to actually penalize it, because he could then actually pay, he was paying for that obviously, but he could pay depending upon the prevailing tariff system, and the prevailing tariff system was not very difficult tariff system for the consumer. Similarly, that he has to maintain a plant load factor of 62.5%, and there was no guideline regarding that when he should maintain this plant load factor at any time of the day. he can connect his generator and supply power to the system. So now, if the situation is such that the power company, what he can be somewhat clever. How? He has his own demand. So during the peak period, he is running his generator to supply his power to supply his consumer, and at the same time he is drawing power from the system to supply it consumer as well. So what is happening? Because he is drawing somewhat extra power, the system frequency is now decreasing because there is limited supply and more power is being drawn by the consumer, bulk consumer, and bulk consumer by drawing that power is supplying its load. So in this way, bulk consumer, it is not increasing its power generation capacity and exploiting the system by taking power from it or purchasing power from it. It is delivering. He is paying for that power, but he is actually drawing power at a time when the system frequency, his system is already heavily loaded. He is drawing more power, means now frequency is decreasing. Similarly, this particular consumer who is having some generation as well, what he can do? He can run his generator and deliver power to the system when the system demand is less. Say during night time, he is generating power and delivering power to the system and pushing, that means injecting power into the system. As a result, what is happening? System was not in demand of power then because system load is then less. Then load is small load then because during night time the load connected to that power company, that is also somewhat reduced. Obviously, load connected to the overall system is also then much less than the normal load. So now during this time, when the system load is somewhat less, system frequency is on the upper side, then this particular generation company say it is injecting power into the system. So what will happen? Since it is injecting power into the system power supply is then more, it is more than the demand. So frequency will increase. So because of these reasons, what happened in the earlier days, before say 2002, there was heavy excursion of power frequency. As I told you, maybe some 52 hertz and 247 hours. During peak load period, it may be as low as 47 hours. During poor load period, it may be as high as 52 hours. So this was the situation. Okay, to get rid of this situation, a tariff system has been devised by our authority, electricity regulating authority. Okay, they have actually proposed or implemented a new type of tariff. This is called availability based tariff. What is this availability tariff based tariff? Availability based tariff, that's why it's called ABT. It is connected to frequency. That means what should be the price of power, price of energy, it is connected with the frequency. How it is connected? If you draw extra power when the frequency is above normal frequency, then you will not be getting any price for that. It will be such that how much you will be earning by delivering power, that will be reduced at higher frequency. Okay, if you deliver power when the system frequency is above 50 Hz, then you will be getting very small return. Not only that, if the frequency is above a certain value, then you will be getting no return at all. You will be getting no price at all for that power, for injecting that much of power. Okay, could I explain? Because that means when the frequency is above normal, then if you supply power to the system, you will be getting much reduced revenue. Not only that, if the frequency is above some other predetermined value, then you will be getting no return at all. You have to inject power without getting any revenue. Similarly, if you draw power from the system, what power? This is undeclared power. You have not previously booked this amount of power and you are drawing power from the system. If you are drawing power from the system when the system frequency is already low, then you have to pay a very heavy amount for drawing this power. Okay, that the power price will be such that it is penalizing price. Okay, so nobody will be interested to draw power at that time because they are bulk power company. They cannot use some hooking system. They will have to pay for whatever they are drawing. So they will be discouraged or they will be penalized if they draw undeclared amount of power, any undeclared power during a time when the frequency is already low. Similarly, if they draw power, undeclared power, when the frequency is above normal, then they may draw power even for free also. That means if the system frequency is above normal, you may draw power without paying price, any price for that. You may get power at free also. But if you inject power during that time, again you will not be getting any price for that. So above normal frequency condition, if you inject power, you will not be getting any price. If you draw power, you have to pay no price. Below normal frequency, if you inject power, okay, you will be getting higher revenue. Below normal frequency, if you draw power, you have to pay penalizing amount of revenue. So this has actually this type of regulation, this type of tariff. This is called the three-part tariff. Actually, the whole tariff I have not discussed here. This is not recorded. Also, the basic concept of ABT that I have discussed here. Basically, if you draw power when the frequency is below normal, then you have to pay more price, and that price is penalizing price. But if you inject power during that time, undeclared injection, obviously, previously you have not declared for that, then you'll be getting rewarding price for that. Okay, because you are helping the system in restoring its frequency because frequency is below normal. Why it is below normal? Because the generation is less. Now anybody who is supporting generation will be rewarded. That's why you will be getting rewarding price. At the same time, if anybody is drawing more power now, he will be penalized because he is responsible for bringing the system frequency below normal. That's why he will be penalizing. Okay, similarly, when the frequency is above normal, then anybody who is drawing power is supporting the system because by connecting more load to the system, he is helping the system to bring the frequency back to normal value. That's why he will be rewarded. How? He has to pay no power price for getting power. Okay, can get power for free also. But anybody who is injecting power from his generator, then he will be penalized. How? Because he will be getting no price, and nobody will be interested to actually inject power without getting any price because for generating power he has to pay price. He has to pay for his fuel. So nobody will be interested to do that because of this actually ABT, availability based study. This is called availability based study because frequency is an indicator regarding the availability of power. When the frequency is more than above normal, it indicates that there is excess generation available. When the frequency is below normal, it's an indication that the our availability in the system is less. That's why it's called the availability based tariff. Because of this availability based tariff, which has been implemented in 2003, frequency has drastically improved in our system. So, if you see the frequency excursion in our system before 2003 and after 2003, you'll see that there is a huge difference between these two. Okay, previously there was much variation in the frequency of the order of say 5 Hz. Now you will see that frequency variation is very small, and this tariff is one of the most we consider important reasons for this close variation in frequency. There are other reasons, of course. What are the other reasons? Other reason is that the whole system, our total system, is now connected through AC line. Now, total power system in India is connected to AC line. And larger the interconnection, better is the frequency regulation in any system, because more and more rotating machines are connected together, more and more inertia are connected together, and for supplying any newly connected load, the power can be supplied by extracting the energy of those rotating inertia, rotating mass. Okay, that's why larger the size of the system, that is when more generators are connected in parallel, better is the frequency regulation. Since from 2014, the total AC interconnection was complete in our system. Interconnection started in that larger interconnection. Regional actually networks were connected together. That again has started after 2003. Why 2003? Because of that electricity bill. Okay. So from 2003 up to 2006, there was interconnection, and this interconnection was three using AC lines between east, west, north, and south. Okay, all sorry, east, west, north, and northeastern region were interconnected through AC line, and southern region were interconnected by DC line between southern region and all others, that interconnection, total remaining interconnection, that was connected to DC line. But from 2014, southern region was also connected to AC line. So from 2014, there is a single frequency everywhere in our network. Frequency, if you measure anywhere in our system, say you are measuring in Kashmir, or you are measuring in Manipur, or you are measuring in Karnataka, everywhere the frequency is same. Why the frequency is same? Because now the system is connected through AC lines. Okay. Previously, southern regions before 2014, southern region was having a different frequency. Why? Because southern region were interconnected. That was interconnected through DC line with the remaining Indian system. Okay, because of this huge interconnection and because of this ABT based tariff, okay, the frequency excursion in our system is within a very small narrow zone. We can say that now the frequency control is in a much better situation in our country. That is because of that availability based tariff. So that ability based tariff, you can say that it is also a part of frequency control of our system. Obviously, for final frequency control, for restoring the frequency back to initial value, you have to depend upon that supplementary control. Otherwise, it cannot be done. But excursion is much less. Okay, and why it is much less? Because there is no undeclared transaction of power. Okay, previously there were undeclared transaction of power. That's why frequency excursion was to a wide range. Now, after implementation of APT, undeclared transactions are much less, because if you drop undeclared power, then you have to pay penalty. If you supply undeclared power, then you have to pay penalty. Okay, and how much you have to pay, that depends upon the frequency. That's why the name is availability based tariff. If you support the system by drawing power, undeclared power, when the frequency is high, then you will be rewarded. You may get power even for free. But if you supply power during that time, undeclared power that you have not declared, that you will be supplying during that time, if this is the situation, then you will be getting no power, no price at all. Similarly, if you supply power when the power system frequency is much less, if you supply undeclared power, then you will be heavily rewarded. You will be getting more price for your power you are injecting, because you are helping the system. But if you draw power during that time, then again you have to pay penalizing price, because you are responsible for making the system frequency low. So this is the principle of you can say that availability based tariff, and this we can say that is a price based frequency control in our power system, that is in operation, and that is in operation from 2003. Okay, so any question regarding this? This is only to give you some idea how frequency is maintained in our system, apart from other frequency control mechanism which includes technology, this is not including any technology. This is basically a commercial approach of maintaining the frequency in our system. Okay, is it clear to you?
Yes, sir.
So with this, we shall have completed the frequency control, excepting for the fact that some numerical examples are to be discussed. That I shall discuss in our next class. Okay. Now, before I complete or close today's session, it is better if I start discussing the next topic, which is the system stability. Okay. So let us have some initial discussion power system stability. 10-15 minutes I shall
Sir,
discuss.
just one.
Yes.
We have a lab from 6. Can you just leave us by 5:55? In that case,
I could not follow.
we have a lab from 6 o'clock, sir. Can you leave us
Oh, lab at 6 o'clock.
5:55?
Okay.
Yes, sir. Just
Then,
informing you, sir.
if you now what is the time? Actually, in my clock, it is
It
now.
is
What is the time according to you when we want to
it
leave?
is 5:37, sir. We can do 15 minutes more, and then, sir,
15
15
minutes
minutes.
more. That is 5:37. Okay. Say it is
Yes, sir.
5. So I shall be continuing for 15 minutes more and then leave all of you. Okay. So everybody will be, I shall
Yes, sir.
stop
I
after
think that will
15
be okay.
minutes. Okay, so no problem. So now power system stability. Hmm. What is power system stability? Power system stability means, okay, already I have mentioned that while discussing the frequency, when I was actually discussing the modeling of generator and load, okay, perhaps I have mentioned that delta F, there was one expression such that 1 plus delta F by F square. That was approximated as 1 plus twice delta F by F. If you remember, if you can remember, this was how we have actually written 1 plus del F by F square as 1 plus 2 delta F by F, and del F square has been eliminated, has been neglected. Why del F square has been neglected? Because we assume that change in frequency is very small, so small that if we actually take the square of del f square by f, because f is say 50 hertz in our system and del f is usually very small, so del f by f will be still smaller. It will be so small that del f by f square will be negligibly small. This was our assumption in frequency control. Why this was our assumption? This was our assumption because frequency of a system can be controlled if and only if change in frequency is very small. If change in frequency is quite large, okay, then you cannot control the frequency because then it is not a problem of frequency control at all. It becomes a problem of maintaining the synchronous operation of the power system. And the problem of maintaining the synchronous operation of power system is called the problem of stability. That means, what is power system stability? Power system stability means it is the ability of the system to maintain synchronous operation. Okay, this was the older definition of power system stability. People then define stability as ability of the system to maintain synchronous operation after a disturbance. Why disturbance? Because after a disturbance only, okay, the question, the problem of maintaining the synchronism that appears when a disturbance occurs. Because when a disturbance occurs, that when disturbance of active power occurs, then only the frequency changes, then only the speed of generator changes. Okay, so previously people defined stability as the problem of maintaining the synchronous operation of the generators in power system. Okay, this is how stability was defined in older days. Why I say older days? Because now the definition of stability has changed a little bit. How it has been changed? Now, this is not only the problem of maintaining the synchronous operation, because The stability of a system may also be lost because of the problem of voltage as well. Previously, it was identified that stability of the generator can be disturbed or may be disturbed by the inability of the synchronous generator to maintaining synchronism only. That's why it has been defined as the ability of the generators of the power system to maintain synchronous operation after a disturbance. But later on, it has been found that stability will not be lost only by the inability of the generators to maintain synchronous operation. It may be lost because of the ability of the system to maintain voltage as well. So there came another type of stability, that is called the voltage stability. So now, how we can define stability of the power system? It is the ability of the system to maintain integrated operation, rather not the synchronous operation, integrated operation after a disturbance. And that disturbance may be on both ways. Maybe the disturbance in respect of active power variation, maybe the disturbance in respect of reactive power variation. Okay, so now we can say that there are actually broadly two types of stability problem. One is the stability problem of synchronous generator, that sometimes is called the rotor angle stability. Another is the problem of maintaining the voltage. And people have identified that the problem of maintaining the voltage is not of the generator. It is the problem of the load, basically, dynamic load. Dynamic load means basically the motor load. So, voltage stability basically is a problem of stability, a problem of maintaining stability of the load, and angle stability or rotor angle stability is basically the problem of maintaining the synchronous operation of power system. So previously people were actually bothered about the angular stability or synchronous generator stability only. Why synchronous generator stability only? Because then people have not encountered the stability problem due to load. Then voltage stability was not apparent at that time. Why voltage stability was not apparent at that time? Because then the system was not that heavily loaded. Why they're not that heavily loaded? You see that our system has actually increased in size everywhere. Load has increased, generation has increased. But basically, what happened with the increase in load and increase in generation, there was no matching increase in the transmission capacity. So, what happened? Day by day, actually, there was a growth in the load, there was growth in the generation as well, but there was not matching growth in the transmission capacity. As a result, what happened with time, with the passing of time, what happened? Our transmission system was getting more and more heavily loaded, and after the transmission capacities were getting more and more heavily loaded, the voltage problem has started appearing. And then people have identified the problem of maintaining the stability of the load, or the so-called voltage stability problem has been identified. So the problem of stability means the problem of maintaining integrated operation of a power system. Okay, interconnected operation of a power system, integrated operation of a power system after a disturbance, and that disturbance may be in respect of disturbance of active power, this disturbance may be in respect of disturbance of or deviation of reactive power as well. Okay, so broadly you can say that we can classify stability in two ways. One is the rotor angle stability, or the stability of synchronous generators, and the stability of load, that is called the voltage stability. Okay, so rotor angle. So this is the broadly how we can define stability and how we can classify stability. So obviously, since this is the older stability, rotor angle stability was the basic form of stability previously understood by people, and we shall be actually discussing this stability only. not the voltage stability, but somewhat some discussion regarding the voltage stability. Obviously, we shall make that is on the simple discussion of stability. I shall only make, not the details discussion. Okay. So when we shall be discussing stability for this particular subject, we can say now we shall be basically referring to the rotor angle stability, and that rotor angle stability means the stability problem because of unbalance between the active power generation and the active power demand. So this stability, rotor angle stability, what is responsible for that? It is the unbalance between the active power generation and active power demand. When that unbalance is very small, that becomes the problem of maintaining the frequency. When that unbalance problem becomes somewhat larger, then it becomes the problem of maintaining the stability of the power system. Okay. And depending upon the magnitude of this disturbance, we shall be classifying the stability into three major types. One is called the steady state stability, then it is the dynamic stability, and then it is the transient stability. Okay. So we shall be discussing thoroughly the steady state stability, dynamic stability, and transient stability. But mostly we shall be discussing regarding the steady state and transient stability, because dynamic stability is somewhat more complex. Analyzing dynamic stability requires more complex analysis. So that's why we shall be restricted to steady state stability and transient stability. So since you have some laboratory class today, okay, I shall be leaving here today, and we shall continue from this phase in our next class on Tuesday. Okay. If you are having any question, you may ask me. Anybody is having any question? Otherwise, I shall be calling, making roll call. Abhi Chatterjee. Abhi Chatterjee. Aditya Rai.
Yes, sir.
Omrita Datto.
Yes, sir.
Anirudh Anand.
Yes, sir. Sir, I was also present in last two class.
Last two class. Anirudh.
Yes. Yes, sir.
Okay. Then Ankit Jaiswal.
Yes, sir.
Arnav Pal.
Yes, sir.
Dipten Mardi.
Yes, sir.
Konishko Bashak.
Present, sir.
Kaushik Maji.
Yes, sir.
Parvez Musharraf Sheikh.
Yes, sir.
Then Pratik Mishra. Pratik Mishra. Then Ritam Amaru.
Yes, sir. Yes, sir.
Then Shomiron Bagdi.
Present, sir.
Chandip De.
Yes, sir.
Shankho Mitra.
Yes, sir.
Shreyas Khatri.
Yes, sir.
Shreyas. Then Sheikh Muhammad Sohel.
Yes, sir.
Sheikh Jishan Rahman.
Yes, sir.
Somnath Pal.
Yes, sir.
Sৌগত Debnath.
Yes, sir.
Saurabh Burman.
Yes, sir.
Shubhadeep Bera.
Yes, sir.
Ujjwal Haldar.
Yes, sir.
Anybody else? Abhi Chatterjee, he did not respond. Okay. Okay, thank you then.
Thank you, sir. Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.